Hello students, welcome to Math 3410 Differential Equation. Lesson 1b is the real starting point of this course. There must be some students who skipped Lesson 1a altogether or a great majority of it, and that's okay. If any need arises, you can always go back to Lesson 1a and study any part of it in any order. Otherwise, let's begin. Let's begin with these three motivating examples, all of which came from our textbook. The first model is Newton's law of heating and cooling, and this is a differential equation. We have the derivative function here related to the original function, and in this equation, our job is to find out the original function, capital T of t. Here, capital T is a temperature, and small t is time. And this TA represents the ambient temperature. Let's analyze this equation. If you have some hot object, some cooked turkey coming out of oven, and you're cooling it. No, you want to serve before it cools down. So, okay, get some freshly baked cake, and then you're cooling it. Okay, that makes a little more sense. In that case, capital T is much higher than the ambient temperature here. So this T minus TA is positive and multiplied by negative R, so entire quantity is negative, which means the derivative is negative. Consequently, the temperature will be decreasing. It'll decrease down to the ambient temperature, and if it reaches very close to ambient temperature, then T minus TA will become very close to zero. Consequently, what we have here, the derivative here, the rate of change will get very, very close to zero. Consequently, the decrease will slow down. On the other hand, what if capital T is less than TA? In that case, you're throwing cold turkey before doing anything. In that case, T minus TA is negative, so multiplied by negative R, this whole thing is positive. So the derivative is positive, so the temperature will be increasing and increasing toward the ambient temperature, and the analysis remains the same because this will get very close to zero. Consequently, the derivative will get close to zero, so very slow increase. So early on, when the temperature difference is huge, then the derivative is big in absolute values, so we have quick drop or quick increase of the temperature, but later on it'll slow down. That's the kind of analysis we can do to the equation. And you can always do those to all the equations you're going to see. This is just motivation example, and I'm taking a bit more time, a little bit more extra time explaining that. Now let's talk about the analysis of solution. By the way, I'm not asking you to solve the equation now and get the solution. Not just yet. That's something we're going to start from next week. At this moment, let's focus upon the analysis of solution. So here's a solution, and it's an exponential model. Let's see, if t gets really big, then we have t to the negative infinity here, e to the negative infinity here, so this whole thing will become zero. So that part will drop out. And what do we have? The temperature will be very, very close to the ambient temperature, and that makes perfect sense considering our common sense. And then C is constant. So whether it's positive constant or negative constant depends upon the initial stage. You see, capital T had been higher than the ambient temperature. Then capital T has to be bigger, so this C has to be positive and remain constant. So the exponential will go down to zero, but stay positive. So the temperature cooling will never go down below the ambient temperature and rise back up. That's not going to happen. You know, you can analyze a solution and you can deduce a lot about the behavior of the model and compare it with the physical system. One final analysis is left. We talked a lot about physics. Now let's talk about mathematics. Is this really a solution? Let's check. Let's check the derivative and see if this is right. Well, let's take the derivative. Let's take the derivative of this. Then derivative of constant is of course 0. And then exponential function always remains the same. And by chain rule, we have to multiply the derivative of the inside. What is it? It's negative r. So I have to multiply by negative r. And you can drop out that 0. So that's a derivative. And we can analyze like this. Factor r out and keep this exponential here. And then we add and subtract the same thing. So what do you have? Exponential plus ambient temperature. What is this? That's the same as this original. See blue highlighted part? So this whole thing is equal to negative r times t of t minus ta. And that's precisely what we wanted, right? So yes, it is a solution. We just checked it. Let's go to the next model. This is radioactive decay model. And you can analyze similarly how this derivative rate of change is related to remaining radioactive materials right now, things like those. And is this really a solution? Excuse me, is this really a solution? Exponential model. Put it over there and check. Very similar to the previous problem, except it's a little bit easier. Next example, that too came from Newton, Newton's law of motion. As a matter of fact, another famous way is F equals ma, where a is the acceleration. So that depends upon time. And F is force. So mass times second derivative of linear position. First derivative is velocity, second derivative is acceleration. And then divide by m, then that's what we have over there. Now, if the external force is given as time of t explicitly, then this is really easy equation. All you have to do is to take the antiderivative twice. Second derivative to first derivative, and then to the original, we take the antiderivative twice. Each time I take the antiderivative, we have an integral constant. First, we got capital A. Next integration, I got capital B. So we have two constants to determine. In order to determine two unknowns, we need two equations. So two equations, we can get those from initial condition, S of t0, something, and S prime of t0, initial time, that's something. So we have two equations here, 1 and 2, and two unknowns, capital A and capital B. We can solve those. So if we have initial position and initial velocity, or equivalently speaking, initial momentum, then you can completely identify the solution. So your entire system is deterministic here. But there's a bit of a problem. What if your F, capital F, is not just a function of t explicitly given, but it is related to current position and velocity as well? All those kind of things are intertwined. Then what? Now we have a serious challenge, and we'll have to do some problems like these later in this course. Of course, you'll do a lot more like these in physics classes. By the way, it's not a coincidence that all three motivation examples here came from physics. Historically speaking, the development of this field, differential equations, and as a matter of fact, entire calculus, by the way, has a lot to do with physicists trying to model the law of nature. And then it's so, and their modeling is so successful that that technique is adopted to other fields of science. So nowadays, differential equations are being used in all kind of other scientific fields as well, like medicine or biology, social scientists, all kind of things. But if you go down to history, most of them came from physics, as a matter of fact. Therefore, we're going to be using a lot of terms that physicists created, like initial conditions. So if you measure some physical system, then initially you measure some position, velocity, momentum, and things like those. And those are called initial conditions at time 0 typically. And also we're going to consider something called boundary conditions. Well, if we have a string making sound and toward the end they are attached, those kind of situation, well, in between we have some motion of that string and creating some sounds. Again, we're going to be using the same kind of term that physicists created, boundary condition, and so on and so forth. Most of the time, our independent variable will be t, representing time. There are exceptions, of course. All right, those are motivating examples, and we even talked about a little bit of history as well. Now, here are some examples of differential equation. What kind of equations we are going to focusing upon? An equation of one or more known functions and their derivatives put together are called differential equation. And here are some examples of ordinary differential equation. Ordinary, what do you mean by that? We have only one variable, single variable functions, so the derivatives are just usual total derivatives. The first example here, d squared x dt squared, second derivative, or equivalent to x double prime, and dx dt, equivalent to x prime, and so on and so forth. First equation is an example of a linear equation. Linear, ODE. What do you mean by linear? First degree. Look at the original function. Is there square or cubed or square root or transcendental or anything? No, it's just first degree, linear. Derivative function, again, just first degree, linear. Second derivative function, again, linear. All those original and derivative functions are linear, and we call it linear ordinary differential equation. Now, what about these functions of t, coefficient functions we call? Those are okay. T cubed, that's not linear. It's okay. E to the 2t power, that's transcendental. It's okay. As long as all the x's are linear, we call it linear differential equation. Next example here is not going to be a linear. Here we have third derivative, but it's squared. So it's nonlinear. Another one, y squared, nonlinear. How about the third example here? We have two functions here, x of t and y of t. So if we have two functions, then typically we're going to be using two differential equations and form a system of differential equations. But we have only one equation, so it's highly unlikely that we can do anything about this equation, except that it's just a first example. If you have two or more functions put together, then the chance is you're going to be required to find some other equations and form a system. Those are examples of ordinary differential equations, and those are the kind of things that we're going to focusing upon. These are examples of partial differential equations, and those are, let's see, differential equation 2 will still be an ordinary differential equation mostly, maybe some dynamical systems. Partial differential equations will be a course of itself, and I don't know whether we'll have a chance to talk about it in undergraduate level. These are some examples of partial differential equations. As you can see, we have multivariable function, and the derivatives are partial. In this course, we are not going to be dealing with any partial differential equation at all, so let's spend about 2 to 3 minutes in the first day, because we are never going to come back to any of these. Okay, The first example is called Laplace equation, and that models, well, a lot of things, but one of the more famous example is electrostatic system. So there's no influx of electricity coming in or out, and how the electricity is going around in static objects, within that object, in the surface, inside, and so on. Next example is heat equation, and it is related to Laplace equation because, as you can see here, this thing over here is repeated here. So it is related to Laplace, but not exactly the same. It models how the heat is flowing in all three directions here, because we are dealing with 3D systems. So we have x, y, z, three space variables, and time t. So we have multivariable function here. Next example is wave equation, and this is again 3D. For example, sound wave propagating, those kind of things. And the last example here is an example of Schrödinger equation, a simplified version, but I'm not going to talk too much about it. It's quantum mechanics, and my knowledge there is limited, so let's leave it at that. All right, those are examples of partial differential equations. The reason I took so much time about partial differential equation today, right now, is because this is the only time. We're never going to come back to partial differential equations ever again. That's why it took some time. Otherwise, we're just going to move on. Let's focus upon ODE, ordinary differential equation. So whenever we say just an equation here in this course, we're going to be talking about ordinary differential equation. The general form is kind of like this. We have original independent variable t, typically time, and original function that we are going after, and then a bunch of the derivatives put together, intertwining as one equation. And of course, our aim is to find out the original function. How do we do that? Slightly less general form, so that y to the nth power, not y to the nth power, nth derivative is explicitly out, but still that's not what we are looking for. We are looking for the original function y of t. And how do you solve those? Well, that's something we'll have to discuss. All right, so much for the introduction of introduction, and we'll meet again in section 2 in a separate video.